This talk is about grading on a curve. The idea of grading on a curve means that the professor either adjusts the letter grades to a different scale, such as the original exam scores, or adjusting the original scores to reflect a more traditional scale, such as 90% to 100% being an A, and so on. Regardless of which method is used, the effect is essentially the same. The need to adjust the grades or the scores could arise from a mismatch of teacher and student expectations regarding the difficulty of the exams. If the class as a whole does worse than expected, it is usually because the test was assumed to be too difficult. Some teachers, on the other hand, purposely write hard tests, and they do that with the intention of curving at the end of the class. The term grading on a curve may have come from grading against a so-called bell curve. This distribution is also known as a Gaussian distribution as well as a normal distribution. And what we do is we use this distribution to determine the cut points that would yield certain percentages in the class that would get A's, B's, C's, and so on. In fact, many actual distributions of the scores are not bell-shaped, but other distributions, sometimes highly skewed, we may get into later on, highly skewed distributions. But in spite of that problem, uh, the uh, the method of grading on a curve has remained fairly popular. Definitions. We will use the same definitions for typical letter grades. For example, we will use A to stand for excellent, B to mean good, C is typically referred to as satisfactory, the letter D is often considered poor, and then the letter F or sometimes E is considered to be a failure. Okay, and sometimes when a student gets an F, they have to retake the class. Uh, so those are very common in the United States and perhaps elsewhere in the world. These grades can be further broken down into a plus and minus category. For example, we could have B plus to reflect that the student actually earned a higher B than your regular straight B. Score distributions give the distribution of scores for a particular exam or final average. The normal distribution, as I said before, is also known as the Gaussian or bell curve, is often assumed, and again, this may or may not be justified. The normal distribution has two parameters. One of the parameters is called the population mean mu. It's written here as this is the Greek letter mu, and the other population or the other parameter of the distribution is the standard deviation. Okay, and I'll typically use the capital letters SD to refer to the standard deviation. More commonly, the standard deviation is written as the Greek letter sigma. Often the normal distributions are indexed by its variance, which is sigma squared. We will not use that notation too often in this talk. Normal distributions are typically abbreviated in using this common type of notation here. So we have XI, which is, an ith student's exam score. All right, so that's what that's referring to. And we're saying that all of the students together tend to be distributed normally here. So this little squiggly symbol refers to the expression is distributed as the capital N is normal, and then we reserve the first position here to be the mean, and the second position here is the standard deviation or variance if you're if you're using that notation. This means that the scores xi written in this fashion here have a distribution that is normal with a population mean 50 and a standard deviation 10. Now let's look at traditional or standard grading schemes. Many students in classes typically get assigned a letter grade of A, B, C, D, and F, so on. And the letter grade that they earn is determined from the percentage of problems in the course that they answer correctly. From grammar school onward, the percentages that get translated into these grades are typically, for example, 90% to 100% as yielding an A, and 80 to 90% is yielding a B, and so on. Sometimes the teachers overestimate the ability of the students, so the grade distribution can fall below the desired grade distribution using the traditional methods. For example, we could have the desired distribution on the left, right here, which has a mode or a peak around 80 and a standard deviation of about 10 units or 10%. Okay, so that's what the teacher is hoping the students will perform at. And let's assume that the teacher administers the exam and then grades it, and lo and behold, at the end, the teacher discovers that the students only scored with a distribution whose mode was 65, the standard deviation was the same. So if we were to use the scheme in the previous slide, where say students who earn 90% to 100 get A's, then we see here that relatively few patients will get an A, and also relatively few patients will get B's. Okay, now how are the proportions determined? Well, this is typically the percentage of students that earn a particular grade, say 80 to 90 being a B, would be the area under the curve. We'll look at this a little bit more later on. Okay, so what happens here is we'll discover, I think it was about 70% of the students get a D or worse using the traditional scheme. So that's the nature of the problem that we're looking to correct. Okay, so here is the breakdown of the letter grades. On the left here, if we actually had a distribution of exam scores according to the left distribution, then 14% would earn A's, 35% would earn B's, and 35% would also earn C's, and so on. But in fact, as the distribution came back after grading, we discovered that only 6.6% of the students would get A's, 6% would get B's, and 24% would get C's. And again, 70% of the class would get a D or worse. So a professor using the traditional grading scheme will discover a grade distribution that could be unintended. If the professor desires to adjust the scores or the grades to get a grade distribution closer to the left distribution, there are several options. One procedure is to standardize the test scores and use cut points based on a normal distribution. To standardize, what we would do is we would calculate a z-score, say zi for the ith student here, and that is related to the student's original exam score xi, and we would subtract the class average x bar from it, and then divide by the estimate of the standard deviation, population standard deviation, which is S. Okay, or you could just say that this is just the class standard deviation. Right, so you get these exam scores, and for example, what we could do is we could say that is if the standard score is 1 or more, then the student earns an A. What does that mean? That basically means that if the student scored at least 1 standard deviation above the mean, then they get an A. Okay, and you can look at the Z range here as well as the X range, the original. So using the original exam scores, this Z is equivalent to the XI's being greater than the sample mean plus 1 standard deviation. Okay, and under that scenario, then we would expect about 16% of the class to get A's, 34% to get B's and C's, and 14% to get D's, and 2% to get failing grades. So that would be most people would consider that to be a relatively generous grading curve. The grade distribution may not be exactly the original targeted distribution, but it may be close enough that the professor goes ahead and accepts these scores as determining the grades. So that's one way to do that. And if we look at it graphically here, here's our distribution colored out. Okay, in terms of the A's. Okay, so if you the mean, okay, is 65, so you can see here that in order to score an A, you had to score 1 standard deviation above the mean, 65. Okay, and the standard deviation is 10. So that means if the student scored 75 or greater, then they get an A. And then if they're between 0 and up to 1 standard deviation above the mean, then they get B's and C's and so on. So that's one way to grade on a curve. Now you notice here that we're still using the original exam scores, the X's. Okay, so so here you see 65, forms the border between the C's and D's, whereas in other approaches, what some professors prefer to do is to translate these scores into the more traditional values. So if a student is bordering between, say a B and a C, then they want this value of 65 to be closer to what would that be? B's and C's. That would be around 80, typically 80%. Okay. So anyhow, this is the way I remember doing it in graduate school. It's fairly easy to get the statistics that you need from a computer package, and then you just mark it, and go down the list of grades and refer to a small sheet, okay, to see where the student lies and assign the grade accordingly. Another way to grade on a curve is to apply a function to the original raw scores, call them xi, so that the transformed values yi have a distribution that conforms to the desired characteristics of the intended distribution. For example, we may want the yi's to have a mean of 80 and a standard deviation of 10. Let this function be denoted by g, so that yi is obtained from the xi's, the original scores, through the function g. We would often call the yi's the adjusted scores. In order for this to be considered a fair conversion, we need to require that if the xi's are less than, say, xj, then the transformed values for students I and j are maintained. The order is preserved. That is to say that yi is also less than yj when xi is less than xj. As long as the function is linear in nature and applied to all of the students, then the shape of the distribution in X will not be distorted in Y. It is just a rescaling or shifting of the original X's. When I say rescaling typically means that you're either compressing or stretching out the scores, but you're doing it uniformly across all of the scores. And then shifting is basically just sliding the entire distribution rigidly either to the right or to the left. This is also considered fair. That is to say, the linear transformation. So that is to say that g is a linear function in the xi's. There are, however, may be considered by some to be a little more controversial, but you can use transformations that do actually distort the distribution in x's. but they do retain the property of preserving the order. Okay, it's a little more controversial, but for distributions that have a high degree of skewness to them, some professors would say that they are actually necessary. Let's look at a review of other methods. The most common method looks at the maximum score and converts this score to 100% by adding a booster to that particular score. The same booster is then added to everyone's score. For example, so let's suppose that we have our original distribution we saw earlier with a mean of 65%. And let's assume also that the class size is 30. Now, in a class size of 30, we would expect that the top scorer would be about 83%. And for purposes of illustration, let's assume that the top score is indeed 83%. Then what we would do is we would solve the following equation. 83 plus boost is equal to 100. And that's just real easy. You just solve for boost, and we discover that boost is 17%. So that's what you need to add to 83 to get to 100 for the top score, and then that 17% is added to everyone's score. Now, when we do that, adding 17% to everyone's score, the class mean jumps from 65 to 82%, which is close to what we desired, which is 80%. And the standard deviation actually is unchanged through adding. So it remains essentially 10 percentage points. Lastly, I just want to point out that what you would do for all of the adjusted scores, the YIs, is you just take the original score and you add the boost, so the same constant. So that's how that's done. The benefit to using the booster method is that it is simple to use and for medium class sizes can work well. A drawback is that the maximum score is an extreme value of the sample depending on one or a few cases. And it is not uncommon for it to be an outlying observation, leading teachers, professors to arbitrarily throw away the top score and use perhaps a more appropriate second or third order statistic instead to determine what the curve of the class is. As the class size gets larger, the probability of getting an outlying student grows, and typically what happens is the difference between the largest score and the total points possible becomes smaller, and that yields less benefit for the entire class. Let's look at the effects of the booster method in more detail. First, let's examine the graph on the right side here, which has the original scores x's along the horizontal axis, and the transformed or adjusted scores along the vertical axis up here. Okay, and this line here is the identity line, so that is the y equals x. So if you were to actually do nothing when you transform your original into the y's, that basically would take any score along the x value, raise it up to the black line, and then go over horizontally till you hit the y-axis. And that essentially mirrors the very same score on the x score. Now, what we're doing here, by contrast, is we are adding a certain number, okay, to the original value, to give it that boost, and we do that uniformly through all of the values of the original scores. Now, to figure out how much do you boost this, boost everyone's score, is you look for the highest score in X, and then you say, well, what needs to be added to that score to get it up to 100? Okay, and that's what determines the boost. And then again, everyone else gets that same boost added to their scores. So that's how it looks geometrically when you look at y as a function of x. Now, distributionally, what happens here is we're starting off with a normal distribution with mean 65. So we can see here that the highest peak is about 65. And when we add a booster to all of the scores, what this essentially does to the distributions, it shifts it to the right by 17 units. I think that's what we used in the on the last slide was 17. So we had over here we had to jump up 17 points from 83 to plus 17 to get to 100, and then over here this distribution would shift to the right by 17 units. So those are just some more details of what happens when you use this particular method. Because of the problems of the previous method, some people have proposed using an average value instead of the maximum value. The average isn't as unstable as the maximum, doesn't depend on the sample size. And as a matter of fact, as the sample size grows larger, using the average value may improve your methodology if you're using the boosting method. So that's another approach to consider. So using that approach, you would use your actual average value in your x, and then you would figure out what the booster is in order to get it to the desired and y. Okay, so that's another another statistic you could use to boost. Yet another procedure could be to find a multiplication factor to each score so that the transformed scores y have also the desired mean. So this is a little different, okay, than what we saw before. And why not mix things up a little bit? So a formula for doing this is given below. So here we have the yi's, the transformed or adjusted scores, and we have a desired mean, okay, in the numerator, and then we have the observed mean that we get from our statistical package from our original test scores, and you calculate the ratio of these two and then multiply it by each student's original exam score. Okay, and to see an example of that using the previous examples, from the last slides, we would use the desired mean of 80, and here I'm getting a little detailed in the distribution. It's not exactly 65, it's 64.985. Okay, but if you put in 65, you'll get roughly the same results here. So we have 80 divided by about 65, and then you multiply it by the original score. And if you calculate this ratio here, that winds up being 1.231. Okay, so you take that number and multiply by each xi. And what happens when you do that? We'll see that in the next slide. The graph on the left presents the distribution and the transformed values of y, or the adjusted scores, from the original values, which had a mean of 65 and a standard deviation of 10. So we can see here that the distribution in the y's appear to us to be fairly normal, and the mean is 80%, which is what we wanted. And that's all well and good. However, there is a bit of a problem here in that the standard deviation may be a bit larger than we would like. All right, we see that when you multiply the distribution in x by a number that's greater than 1, what happens there is you get an adjusted distribution which has a greater standard deviation. And if your original intent was to keep your standard deviation at 10, this may be considered to be an undesirable outcome. So in this particular case, where would you have a problem with that? Well, if you're not very comfortable with having scores greater than 100, we can see that we have a bit of mass, okay, that in this distribution that is higher than 100. In particular, it's about 5.2%. So the chances that a student's grade is going to be higher than 100% is about 5%. And in this particular case, I guess you would be okay if you just truncate, or you could, if you're comfortable with that, just keeping the score as is, and accept that higher than 100% score. Okay, in this slide, what we're doing is we're comparing the assignment of grades from the original distribution. Okay, that's the distribution that had a mean of about 65, and using this transformation, okay, with y being 1.231 times x. So that distribution boosts the number of A's from originally 6.6% all the way up to 21%, and then the B's go from 6 to 29%, and then the C's go from 24 to 29, and we can see that the D's and F's, all right, they go from 38 and 32 to 16 and 5. So I think many professors will be much happier with this assignment of grades for their class, and I'm sure the class would be a lot happier as well, getting this distribution as opposed to the original here. So that's one of the benefits to using this procedure. Let's see here. So following the following distribution may be considered acceptable by many. I agree, and it is very simple to compute, and it can yield good results. With an additional factor, more control can be exerted on some of these distributions that remain problematic. So in this particular case, we kind of lucked out in that we didn't have an excessive number of A's. In the following slides, I'll show you an example where in order to get to the desired mean, your standard deviation winds up becoming much larger, and maybe unacceptably so. And in that situation, you do have a problematic transform distribution. And what tools do we have available to us to remedy that situation? So that'll become our next problem. Okay, so again, the motivation is for what we call a two-parameter transformation. Again, the grading distribution discussed above may be fine, but sometimes the difference in the raw score mean and the desired mean may be so great that the multiplication factor produces too much variability. And let's look at an example. So suppose, for instance, that X, we have the original exam scores are normal with mean 40 and standard deviation 15. If we want to transform these into adjusted scores that have a mean of 80, that using the method that we just described above will also yield a distribution with a standard deviation of 30 percentage points. Because in order to get the mean of X is from 40 to 80, we have to multiply it by 2. We have to take 2 times X, and that'll give us our Y, just using the method that we described. So what does that do to us in terms of grade distribution? In that particular case, the proportion of A's would be 37%, which may be considered undesirable, depending on how easy the exam was and what the professor's expectations were. Maybe the professor doesn't like the fact that this distribution yields that. So there may be a desire to decrease that. That's where we're heading with this. So one way around this problem is to perform what we call a linear transformation, sending 2 quantiles in X to 2 desired quantiles in Y. And the following example can help explain this method. So again, if x is distributed normally with mean 40 and standard deviation 15, then y, which is distributed normally with mean 80 and standard deviation 30, since y is equal to 2 times x. The chances that y is greater than 100% is going to be 25% in this particular case, and that may be considered by some to be absurd if 100% is considered to be a perfect score. And again, the person only has to score greater than 90%, in which case the chances of this adjusted score being greater than 90 is 37%. So instead, suppose we want to transform the x's into the y's so that, again, y has a mean of 80, but we want its standard deviation to be 10. To do that, we can add another parameter to the problem. In addition, we could transform the x's into the y's using lines, again, linear transformations, which is considered to be, quote unquote, a fair way to convert between the two scales. Sort of like going, this is a good analogy, it's sort of like going from Fahrenheit to Celsius or Celsius to Fahrenheit. If you live in the United States, we use Fahrenheit as our temperature. Most people are very familiar with Fahrenheit. So I live near Canada, so when I listen to Canadian stations, I'll hear their weather channel, and they'll say things like, "Well, it's 10 degrees," or it's 5 degrees, or it's well, up here it doesn't get too hot, so maybe they may say it's up to 25 degrees, okay, and you're wearing a short sleeve shirt, so. For some people, they don't know what Celsius is at all. So when they hear that, they're like, I have no idea. But what we do is if we do have an equation, we can just translate, okay, Celsius into Fahrenheit. And so, for example, if the Celsius is 10 degrees, I think that's 50 degrees Fahrenheit. So that's the idea. So what you're doing is you got your X's here, which are the exam scores, which are unfamiliar. And what you want to do is you want to transform those into our more commonly associated scaling. So again, where 90 to 100 is A's and 80 to 90s are B's, and so on. So that's the kind of thinking here that we're going for. Now, in this particular case, we're just doing one line to the whole across the whole set of grades or across the whole set of scores available. So what we do is we can write the equation in linear algebraic notation here. So we got a vector here, y1 and y2. Those are our two desired scores, okay, which can be written as a product of just this matrix times this vector. And the x1 is, for example, some score in x that you obtain again from your statistical package. It could be the mean of your original exam scores, and then x2 could be something that you derive from your statistical package. So you take your mean and you add a standard deviation to it. And if you want to set your borderline between those who are in A's being greater than one standard deviation above the mean, and those who score just a little less, they get B's. Okay, then what you would do is your x2 would be equal to your your class average plus one standard deviation. So that could be another one. Now, what does that mean in terms of your y's? So the average, I believe, is your borderline between B's and C's. So then you would let y be equal to 80, and then y1 would be 80, and then y2 would be 90. Okay, so you have your y1, your y2, your x1, your x2. So the things that are unknown are your m, which is your slope, and b, which is your intercept parameters. Okay, so we need to solve that, and using linear algebra, we get the following solution on the next slide. So in matrix notation, it's written this way, and if I if you go through and you with the product and finish it, okay, you can get two sets of equations here. Your slope, okay, which you probably remember from your high school algebra class, okay, and then the intercept is less memorable, but this is the intercept, okay, for 2 points. That's usually not the way, right? That's usually not the way we solve for intercept. But for this particular problem, that's what we're doing. We're just basically taking 2 points, okay, and connecting them with a line, okay, and then extrapolating that line, to all values that we can see. All right, so M and B are then determined, and then what we do is we transform through the linear function here, M times xi. Okay, so the I student gets an exam score xi. We multiply by M and add B to that, and that gives the adjusted score yi. And it's that simple. And this is all from high school algebra class. We all learn this. Well, a lot of us certainly have learned this, but a lot of us have forgotten it because we don't use it that much. So this is just a reminder. Again, this is not too complicated, and it yields quite a bit of benefit when we add an extra parameter to help us determine a nice curve for our class. So let's look at some examples. So going back to the distribution here now, where x is normal with mean 40 and standard deviation 15. Again, we want y's, we want our transformed or adjusted scores to be normal with mean 80 and standard deviation 10. So when x is 40, when x is the mean, then we want y, our desired mean, to be 80. Okay, so 80 is the border between the b's and the c's. Okay, and then at 1 standard deviation above, okay, that's above the mean. So that would be 40 plus 15 is 55 for the x. So when x is 55, then we want the y to be 1 standard deviation above its mean. So again, the mean for y is 80, and then we want to add 1 standard deviation to that. So that's just 10. So that's y is equal to 90 when x is equal to 55. So really, this is all it is. Just these 2 points here, x1 and x2, and y1 and y2. Plug them into the formulas you saw previously, and you get your value of m and b, and then that becomes your in the yellow rectangle here. That becomes our function that we use to translate the x's, okay, the original exam scores, into the adjusted scores y's. And just as an example to show, I probably should have hit an enter key and pushed this down a little bit, but in any case, just to show it works, you could plug in 40 in here and you get 80 as an output. All right, let's move along. This is getting long, this lecture. So here's the original distribution, okay, x's, okay, distributed normally would mean 40 and standard deviation 15. So what happens here is when you transform these x's into the y's, again, the y's are centered at 80 and the standard deviation is about 10. And so what happens here is the distribution shifted up, and it was also compressed. So that's what happened distributionally. And if you look at it from a transformation or functional form here, what we have is the mean of x, okay, gets boosted by a certain amount that depends on the actual value of your exam score, and gets translated over here into the y's. Now, for the vast majority of students, and let's say they all land around here typically, they wind up benefiting from this curve. Their scores wind up going higher than the identity line here, the black line here. So that's good for those students. But one of the things you have to be careful of is sometimes these lines will cross, okay, and they can cross pretty far down, pretty low, like it could cross around 90 or 85, percent. So under that circumstance, what you're doing there by applying the curve is you're penalizing. You're actually penalizing some of the students for doing really well. So that can be a problem. And I have a very simple solution to that, and that is just to take the maximum of the curved score and their actual score, and just whatever one winds up on top is what that becomes their score. And then I go ahead and just use my typical grading scheme, from that. Okay. Now, when you do that, I should note here, you're not applying the same line to all of the students. So yeah, that's going to yield a distortion in your curve, that, like I was saying before, right? Where you're compressing harder on some sections and maybe stretching on others, right? So you are distorting. But we're doing that in the interest of being fair to the students, right? You don't want to penalize people for being, doing really well, which is typically what would happen, okay, if you were to, apply the same curve to all of the scores. Let me get to my last slide here, just for some final remarks. So sometimes applying the same transformation to the entire class is not fair because it can help some while hurting others. A more complex method is to use the raw data to determine the borders between the grades and then transform those scales to a standard scale for each grade. So that may not make much sense. So again, this is probably better deferred to a future lecture if I ever feel the desire to do that. Okay, so but here's basically my point in a nutshell. So what you could do is, for example, is you could take the A's and set them to be at the top quartile. So you basically tell your students before the class starts, all right, the top quartile of everyone is going to get A's at least. Okay, at least the top quartile is going to get A's. And those who score, between, say, the third quartile and the median will get B's, right? And then what I did for many of my undergraduate classes, for the border between the C's and D's, I went down 1.3 standard deviations below the mean, okay, before a student would get a D. And the thinking behind that is if the distribution of grades are normal, that winds up being about 10%. Okay. And all right, so that's just so what you do here is you go ahead and you get these borders for your various grades, okay, and then within each A grade you go ahead and you transform whatever ranges there are in the A's. You can transform those up to, say, 90 to 100, and the B's could be 80 to 90 and so on. So that's one approach to the problem. I never actually did it that way, but anyhow, going along the lines of what we were discussing throughout most of this discussion, that's how that could be done. Let's see here. So again, like I said, I would suggest calculating a final score from as the maximum of the original exam scores, the raw score, and their adjusted score, so that if they happen to do better without the curve, then go with that. Lastly, and certainly not least, when determining the cut point, I would recommend that you do not include students who do not put in a sufficient amount of effort. This helps to keep the students from relying on a curve to get them through. Now, usually what I did is if any student missed any exam, they were not included as people being sampled to determine these cut points, say, up here. And it's particularly important because the standard deviation is fairly sensitive to outlying observations. And if a student misses an exam, they're going to be really outlying way down towards the bottom, and that's going to inflate your standard deviation, and that may be inappropriate. So you just don't include them. That reduces your standard deviation, and my experience has been that using that approach has given fairly satisfactory results. So I hope this helps someone out there maybe to you know consider alternatives to curving their grades if they feel inclined to do so. Thank you very much.